So I will talk today about Mediterranean ecosystems. We found them in 5 points in the globe, but even if each of one has their own biodiversity, endemic species adapted to fire, we know that all of them characterized by for these long and dry hot summers, and those ecosystems or most of the dynamics of those forests are driven by fires that are the main natural disturbance, not the unique but the main, and it's the main today and will be the main disturbance for the next years too. We don't know much about the dynamics for the future, but we if we want to be prepared for that, maybe we have to start thinking how to make those pine and oaks forests more resilient and more prepared to those big fires. So I will focus my study in the Mediterranean basin, but well, the idea is that the study or the hypothesis and questions apply for all of them. So I pick up Catalonia as a study example, as a region that shares many commonalities for all of them. There are the big part of forests in the Pyrenees, a big plain of agricultural area, lots of urban areas in the coast. Here you see a graphic of the annual burn area in the last 35 years, I think, and the number of fires. So fire regimes in Mediterranean areas or regions are a compendium of factors that go there to produce these big, large fires, this huge amount of burn areas depending on the year. So there are, at least for Catalonia, there's 7.5 million of inhabitants. We have seen the last years lots of rural abandonment, urban sprawl that goes to wildland-urban interface. There's no lot of forest management, or not as before, as 14 years ago. And we have seen these high fire exclusion policies that, well, you know better than me, I guess, the paradox that we bring there. So the idea of here that I want to present today is we can open our forest landscapes with croplands and pastures to see if we can create more resistant or landscape more resistant to fires. So we have two questions. If will fire impacts decrease when the landscape mosaic change, and then but how will be the remaining forest spatial distribution? So we wanted to, or we decided we have to take three decisions. How much natural vegetation has to be converted to agriculture, where to put or to allocate these new croplands, and how the patches of change has to be aggregated in the space. So to answer those questions, I will present the two models I've been using for that. So the first one is a land use change model that has been calibrated to replicate three land cover transitions: urbanization, rural abandonment, and agricultural conversion. The second tool is called MedFire. It is a spatial explicit fire succession model. It simulates a kind of a top-down fire regime, even if the patterns or the fire scars are emergent from the dynamics of the model. There's a specific model or specific process that mimics fire suppression, and there are two critical vegetation processes: post-fire regeneration and scrubland erosion. So I will go, as we are in a resource modeling congress, I will go into detail a little bit for these two models, and then we will back to the questions, to the scenarios and the results. So the first model is demand allocation one. That means that the user has to design the quantity of change, the quantity of new urban areas, or the quantity of new croplands every time step. It has to define or to create or interpolate what I call a transition potential map that indicates where is more likely a change happen. And then I've developed kind of an algorithm to spatialize the occurrence and the contagion of the change. With I don't want to go to the detail of the algorithm, but grosso modo, it has 3 parameters per process that I've parameterized. Okay, sorry. So that's an idea of the kind of spatial patterns I can generate. The density and the size of the changes are driven by these 3 parameters: the intensity of contagion, the patches of change emergence, and the land cover change contagion. So with that, I've calibrated this model for these 3 transitions: urbanization, rural abandonment, and agricultural conversion at 2 scales, 2 spatial scales. This is the log-log size distribution of the patches of change. The full dots are the observed ones, and the empty ones are the simulated. And these are the sets of parameters that best fit the observed patterns. So with this model, I've coupled this model to the netfire model that simulates fire regime. There are 2 distributions that have to be defined. There is the ignitions that now the new capability of the model is that ignitions depend on the agroforest interface and the wildland urban interface. That means that when there will be no new urban areas or new cropland areas, the ignitions or the probability of ignition will vary, because we know that ignitions are more frequent where these interfaces may merge. And that's only the little explanation, or the 2 pictures to explain how regeneration post-fire works and scrapland colonization does. I don't want to go there. So what's new here? It's this the approach to simulate firefighting in the model. So here I show you 2 examples to fires, because now firefighting in the model depends on the landscape configuration and the land cover familiarity. So once I have ignition, the red point, in the model, the suppression will start once the fire front fine or burns as enough strip or agricultural strip. So if once the model burns, or the fire front burns at least, let's say 5 hectares or 10 hectares, it means it's an opportunity for the firefighters to stop the fire, and then everything that goes after that fire front stops. So for example, in the first perimeter, the blue area has been burned, but not the green one, and the same for the second one. So with these 2 models, I can come back to the 3 questions and create a set of scenarios in which we have urbanization, a little bit of urbanization, agricultural conversion, fires, and firefighting. And to answer the questions, how much agricultural conversion, where to put the new croplands, and which spatial pattern, I've done a factorial design in which I've converted per year. I say D is 100 kilometers squared per year, D2 is 50, 2D is 200, and 3D is 300. And I've used 2 extreme spatial patterns, so new croplands areas will be very aggregated or very sparse. And I've created kind of 3 storylines. New agricultural areas will be located in the, let's say, in the more forest areas, or to improve the rural areas. Other ones in critical fire points, and the other ones close to cropland areas or current cropland areas. So these are the scenarios. Some results here. So I've defined the effectiveness as the amount of area suppressed in regarding the target area of each fire, and here are I'm sorry. Those lustrum is 5-year periods. It is I've simulated for a period of 40 years, and for each storyline and demon. Here we start to see where where I put the black line. We start to see a significant increase of the effectiveness. So what we can say here is the effectiveness of these treatments doesn't start at time 0. We have to wait at least 15, 20 years, depending on the storylines, to see an effect of that. Here I wanted to show with these two graphics, at least in the aggregate pattern, that at the beginning, so the black line, green or black line, I don't know, is the observed effective. So if I don't do anything, we don't touch the landscape, that should be the control scenario. The effectiveness is shown by this black line, the horizontal one. And the effectiveness of all the treatments, at least for the aggregate pattern, when the croplands are in big patches, we see that we have to, even if we change 50 or 100 kilometers squares per year, we have the closed, so the effectiveness is pretty the same. And we see that when we cross the 200 kilometers squares demon, the effectiveness is pretty the same too. So we see that we need to at least cover or change a little bit or dramatically, depending on the point of view, the landscape to have an effect on the fire regime. And we see also that when we cross a threshold, there's no increase on effectiveness. So those are the two main messages of this research. And this is the final, let's say, study or result. That's the increase or the decrease, the triangles in green or in red, that mark the increase or the decrease of the forest patch core area, to see a little bit the impact of these storylines or these management actions on the forest. So what I want to conclude for today is we have a challenge of integrate multiple drivers of global change and on tools that allow us to simulate not only forest landscape dynamics, but kind of management alternative for new futures. We have seen that we need to accumulate enough enough management or enough open the landscape to have an impact on the fire regime. So at least for Catalonia, for the current landscape in Catalonia, we have to open the landscapes at least during 15 or 20 years to have a real impact on the fire regime. And we have seen also that at least has to be 200 kilometers per year to really, if we want to reduce fire regime. Of course, this natural vegetation conversion to agriculture has to be taken in with caution and integrated with rural and fire prevention aggregated policies. And we think that these alternative management strategies can inspire other regions in fire-prone landscape or regions. So thank you for your attention. I'm happy for questions.